Okay, so we're going to start with a recap from the previous two lectures. Specifically, we're going to recap some of the points that will help us today in deriving the governing equations for the linearly elastic behavior of an isotropic material. So to start off, to start off with our recap, we found that after applying the Coleman-Knoll procedure that we denoted C and P, we found two constitutive relationships, the first one being the free energy, so we have phi r is equal to phi r hat, which is a function of the Wright-Cauchy-Green tensor, and we also have that TRR, our second Piola-Kirchhoff tensor, is also a function of the Wright-Cauchy-Green tensor. And we found that we showed in lecture 27 that these satisfy the principle of material frame indifference. So we moved to a rotated frame and found that these constitutive relationships satisfy the PMFI. So next we have our free energy imbalance. So we have that phi r dot minus 1/2 TRR double dotted with C is less than or equal to 0. And then by the chain rule, we have that phi r dot is equal to the partial derivative of phi r with respect to C, del C, double dotted with C dot. And so now if we substitute this into our free energy imbalance, we have that del phi r hat del C minus 1/2 TRR double dotted with C dot is less than or equal to 0. However, as we discussed before, if we have this quantity equal to something that is non-zero, then we can therefore find a value of C dot that violates the free energy imbalance. So we are going to restrict that this quantity is equal to 0. So we have del phi r hat C del C minus 1/2 TRR is equal to 0. So now we can form a relationship between our second Piola-Kirchhoff tensor and our free energy. So we have TRR is equal to 2 del phi r hat C del C for hyperelastic materials. And we have that this is our thermodynamic restriction. All right, so the point in recapping this is that this is going to come in handy when we are deriving our governing equations for linearly elastic for the linearly elastic behavior of an isotropic material. So we'll come back to this pretty soon. But next, what we are going to recap is some of our assumptions we make for our linear theory of elasticity. So the first assumption that we are going to make is that the reference configuration is natural. So what does this mean? This means that our free energy has a local minimum at C is equal to 1, or the identity tensor, and that there exists a scalar alpha such that C minus the identity tensor is less than or equal to alpha. So this means that phi r hat of C is greater than or equal to phi r hat of the identity tensor. And then by definition of local minimum that we've learned in undergrad calculus, we know that del phi r hat C, del C evaluated at the local minimum, C equal to 1, is equal to 0. And so then up above, we showed the relationship between the second Piola-Kirchhoff tensor and the free energy. So if the free energy evaluated at C equal to 1 is 0, therefore our second Piola-Kirchhoff tensor and consequentially our first Piola-Kirchhoff tensor and our Cauchy stress tensor are all equal to 0, specifically when C is equal to 1. All right, so that's our review of the natural configuration. Next, we're going to review our second assumption, which is that the deformation consists of small displacements. From the reference configuration. And what does this mean? This means that our, if we take the magnitude of F minus the identity tensor, it's really small. So just a review of what is considered a small deformation. We have some deformation U of X T, and that's equal to the mapping of X comma T minus our material point X. So it's a review of what's considered a small deformation. And then again, as a review, as we discussed earlier this semester, we have our green St. Bernard tensor, which is equal to 1/2 C minus the identity tensor, which we can then rewrite as 1/2 F transpose times F minus the identity tensor. So again, this is our green St. Bernard tensor. And then we know that F is equal to the identity tensor plus H. And so we can rewrite our green St. Bernard tensor in terms of H. So that would be E is equal to 1/2 H plus H transpose plus H transpose times H. And now, as we said before, F minus our identity tensor is really small. So we can take the limit as the magnitude of H approaches 0. And so then we get that F is equal to the identity tensor plus some higher order term that we'll later neglect, but we'll keep it in our equation for F right now. So then if, as we take our limit as H approaches 0, we also have our infinitesimal strain, which is equal to 1/2 H plus H transpose. And so these equations will come in handy in just a bit when we start deriving our equations for our governing equations. But before we start deriving our governing equations, we first need to define our elasticity tensor. So our next section is going to be the stress strain relationships for small deformations. So everything we did prior to this was just a bit of a recap. And again, everything we just discussed will soon come in handy when deriving our governing equations. But to define our elasticity tensor, we're going to start with the Taylor series expansion. Of for our second Pila-Kirchhoff tensor about C is equal to 1, or our identity tensor. So when we do this, we'll get an equation that looks something of the form of TRR hat of C is equal to grad TRR C times C minus the identity tensor plus some higher order terms. And if we expand out what our grad of TRR is, we have TRR hat of C is equal to del TRR hat of C del C evaluated at C is equal to 1 C minus I. And then again, we have some higher order terms. So from here, we're gonna define this. So using this, we can define our elasticity tensor to be C is equal to 2 times the derivative of the second Pila-Kirchhoff tensor evaluated at C is equal to 1, and we strategically pick this as our definition, and we'll explain a little bit later on why we define it to be this way. But for now, so since we defined our elasticity tensor to be 2 times the derivative of the second Pila-Kirchhoff tensor with respect to C, we can now rewrite our Taylor series expansion as 1/2 C times C minus the identity tensor plus 0 plus some higher order terms. All right, so now that we've introduced our elasticity tensor, it would be helpful to now go through some of the properties of the elasticity tensor. All right, so first we have that our elasticity tensor is symmetric. And in addition, our elasticity tensor is a 4th order tensor, so for it to be symmetric means that Cijkl is equal to Cklij. And so because it's symmetric, let's say we have another symmetric tensor, A, since A is also symmetric, we can now define a new symmetric tensor B, such that B is equal to C A. And in additional notation, this means that Bij, since C is a 4th order tensor, we haveCijkl times A KL. So our first key property is that the elasticity tensor is symmetric. Our next property is that the elasticity tensor is positive, semi-definite, so what this means is that we have our symmetric tensor A. If we double dot that with C times A. This is greater than or equal to 0 for all symmetric tensors A. All right, and then our third and final property is that our elasticity tensor obeys some sort of transformation QT is equal to C times Q transpose A Q. So this proof is pretty simple, so we'll run through it real quick. So suppose our right Cauchy-Green tensor C is a function of T. So we have C as a function of T. Then we're going to assume that C of 0 is equal to the identity tensor, and C dot of 0 is equal to some symmetric tensor A. So we have that our constitutive equation TRR of T is equal to some, we have by our constitutive equation that the second Pila-Kirchhoff tensor is a function of C of T. So now if we apply our chain rule, we have that TRR dot is equal to del TRR hat of C del C times C dot. But then from above we said that the derivative of TRR with respect to C at C equals 1 is equal to, so 2 times this is equal to the elasticity tensor, which means we can rewrite this as 1/2 the elasticity tensor times C dot, which therefore means that TRR dot evaluated at C is equal to the identity tensor is equal to 1/2 C times A, because this was one of the conditions we assumed, that C dot of 0 is equal to A, so we just plug that in. So now if we have that TRR undergoes some sort of rotation, we'll call that TRR star. We have, let's say, we apply some sort of rotation Q transpose TRR times Q. We have that by our constitutive equation that this is that our second Pila-Kirchhoff tensor is a function of Q transpose times C times Q. So now if we take the derivative and evaluate at C is equal to 1, we have Q transpose TRR dot 1 Q times Q is equal to And so now we're plugging in we're now like using our assumption that we stated above. So this is equal to 1/2 Q transpose times C A times Q. And now since A is symmetric, we can then rearrange the order of this to be C times Q transpose A times Q. And then our 1/2 will cancel out because then we can plug in for TRR dot evaluated at the identity tensor, plug in 1/2 C A. So then our 1/2s cancel, and on the left side we have Q transpose. CA times Q. So that's how we show that it obeys this relationship. So if we apply some sort of rotation, transformation, it obeys that relationship. So moving on to now, we're gonna in our next section we are going to provide estimates for the stress and free energy. And this is where the information we recapped at the beginning of lecture is going to start to come in handy. So in the beginning, towards the beginning of the lecture, we defined our natural configuration, which means that we have T hat of C evaluated at C is equal to the identity tensor, is equal to some zero, is equal to the zeros tensor. And then from before, we started off the lecture, or sorry, I take that back. So just above, right up here, right here, we showed the relationship between the second purely Kirchhoff tensor and the elasticity tensor. So we have that del TRR hat of C del C is equal to 1/2 the elasticity tensor. And so again, this is because of our stress-free natural configuration, and then this is we defined our elasticity tensor above to be 2 times the derivative of the second purely Kirchhoff tensor at C is equal to 1. So that's how we got these two relationships. So next, as we did before, we can further write out our Taylor series expansion. So up here we have that TRR hat of C is equal to, sorry, can't see that, 1/2 C minus 1 plus some higher order terms. Now, because we're dealing with small deformations, we can then take the limit as the Green-St. Bernard tensor approaches 0, so we can rewrite this as TRR hat of C is equal to 1/2 the elasticity tensor times our Green-St. Bernard tensor plus 0 times some, or not 0, plus some higher order terms. And so this is as our green St. Bernard tensor approaches 0. So then moving on from before, earlier in our recap, we stated that for small deformations, F is equal to the identity tensor plus some higher order term. And then we know that our the Jacobian is equal to the determinant of F. And this is equal to 1, and then again some higher order term that we'll end up neglecting, but for now we'll keep it in our equation. So now we can form our equation for the Cauchy stress. Which is equal, so we have T is equal to J to the negative 1, F TRR F transpose. So this is equal to, using our definition, and J to the negative 1, because we're dealing with small deformations, it's approximately the same as J. So we have, again, 1 plus some higher order term times F, which is our identity tensor, plus some higher order term. And then we have that times TRR times F transpose, and which is the same as F. So then when we multiply these all together, we have that T is equal to TRR plus some higher order term for H approaching 0. So this is for this case for small deformations. And so now we can also form our first Pila. We can also express the stress tensor in terms of the first Pila Kirchhoff tensor. So we have that TR is equal to J times T times F to negative transpose. So now we can express, so now solving for T, we have T is equal to J to the negative 1, TR times F transpose. So we just rearrange this equation, applied our tensor calculus, like we rearrange this equation just so that we're solving for our stress tensor. And now that's equal to 1 to our Jacobian multiplied by our first Pila Kirchhoff tensor times F transposed, which is again the same as F. Oh, sorry, couldn't see that. So that we then get that T is equal to TR plus some higher order term. Again, for H approaching 0. So now using our definition of the Jacobian for small deformations, we can also define our, so we can also define the density and convectional body force. So we have that the density is equal to the Jacobian times the density in the reference configuration, which is the same as which we found above. The Jacobian is 1 plus some higher order term times the density in the reference configuration. And then for our convectional body force, we have B0 is equal to, again, the Jacobian times the convectional body force in the reference configuration. So again, that's approximately 1 plus some higher order term times B0R. So now, so next, so before we took the Taylor series expansion for the second Pila-Kirchhoff tensor, but now we're going to take the Taylor series expansion for the free energy phi r c phi r hat of c about c is equal to 1, or the identity tensor. So now if we carry out our Taylor series expansion, we have phi r c is equal to phi r 1 plus c minus 1 double dotted del phi r c del c evaluated at c is equal to 1 plus 1/2 c minus 1 double dotted with del squared some function of c del c squared, all that evaluated at c is equal to 1 multiplied by c minus 1. And then we also have our higher order terms that appear in our Taylor series expansion squared. So our Taylor series expansion looks kind of nasty. However, oops, sorry, forgot the R right there. So it looks nasty, but we can simplify it. So we know, so we're going to assume that phi r c, phi r hat of c, evaluated at c is equal to 1 is 0. And then we also have that del phi r hat of c del c we have evaluated at c is equal to 1 is equal to our 0 tensor. And then we have that del squared phi r hat del c squared evaluated at c is equal to 1. This is the same as so we have that from before we said that so from before we have that TRR is equal to 2 times sorry, give me 1 second. So we have, before writing what this is equal to, from before we had that TRR is equal to 2 times del phi r hat of c del c. And then so this we talked about during our recap, but then we assigned our elasticity tensor to be 2 times del TRR hat of c del c evaluated at c equal to 1. So then we have that c is equal to 4 times the second derivative of the free energy with respect to c evaluated at c is equal to 1. So then rearranging this equation, we then get that this is equal to 1/4 our elasticity tensor. Okay, so now that we have this, we can now substitute back into our Taylor series expansion. And we have that phi r of c is equal to 1/8 c minus the density tensor double dotted with the elasticity tensor times c minus 1 plus some higher order terms. And so now rewriting this in terms of as the green Saint Bernard tensor approaches 0, we get phi r hat of c is equal to 1/2 e double dotted with c e plus some higher order term as e approaches 0. So now all of our equations that we defined before, where we had some higher order term, we can just overall neglect all of these for our theory of elasticity, for our theory of linear elasticity. So above, where we have t is equal to TRR plus some higher order terms, we can therefore say, so neglecting all I'm going to write HOT for higher order terms to save some time. So neglecting all of our higher order terms, we therefore get that T is equal to TRR. And then above we showed that T is equal to TR plus some higher order terms. So therefore T is equal to TR. And then we also above defined our density and the convectional body force, so we can say that our density is equal to the density in the reference configuration, and our convectional body force is equal to the convectional body force in the reference configuration. So now from our Taylor series expansion, since we're neglecting all of our higher order terms, we have that our second Piola-Kirchhoff tensor is equal to our elasticity tensor times the Green-St. Bernard tensor plus some higher order terms. But we just said that these are going to 0. But then we showed that our TRR hat of C is equal to TRR, our constitutive equation. But then above we showed that this is equal to our stress tensor. And then we have, neglecting higher order terms, that this is equal to our elasticity tensor times the Green-St. Bernard tensor. So we have the equation T is equal to CE. So this is our stress strain relation. And so then, just to recap, since we're dealing with small displacements, our Green-St. Bernard tensor is equal to 1/2 H plus H transpose. And then above, from our Taylor series expansion, for phi r hat, which is a function of C, by our constitutive equation, we have that's equal to phi r. So this is equal to 1/2 our Green-St. Bernard tensor double dotted with the elasticity tensor times the Green-St. Bernard tensor plus some higher order terms. But again, we just said that these are going to 0. So then we have our free energy equation, which is phi r is equal to 1/2 E double dotted with C E. All right, so these equations, okay, as I just said, this is our free energy. So these will be used these will come in handy for our governing equations, but there's still one last thing we need to define before we can actually form our governing equations. So let's go ahead and start on a new page. So we're going to assume when forming our governing equations that our body is isotropic. So we are going to assume our body is isotropic. So this means that CE is a linear function of E. So next we have, by the representation theorem for isotropic linear tensor functions, we have that CE is equal to 2, and then we have some scalar constitutive moduli mu times E plus lambda times the trace E times the identity tensor. So again, that's by the representation theorem for isotropic linear tensor functions. And mu and again, mu and lambda are, so mu and lambda are scalar constitutive moduli that we actually defined in one of our previous lectures, so that's just a recap. But so now that we have this equation for our isotropic body, we now have the tools to form our governing equations. So the first governing equation actually comes from what we just defined. So first governing So our first governing equation comes from what we just defined, and let me go ahead and show this sheet again. So before we formed our stress-strain relation, so we had that T is equal to our elasticity tensor times our green St. Bernard tensor, which we just defined for an isotropic body is 2 mu E plus lambda trace of E times the identity tensor. So we have our first governing equation. So this is the stress for this is our stress tensor for a body that behaves for a linear elastic body that is isotropic. So it's our first governing equation. And then our second governing equation So to form our second governing equation, we are going to use, using the relationship between the stress and free energy. So let's see. So from our Taylor series expansion, we found that phi r is equal to 1/2 the green St. Bernard tensor double dotted with the elasticity tensor times the green St. Bernard tensor. So we have that phi r is equal to 1/2 E double dotted with CE. Now from above, we can now substitute in what we have for our stress tensor, which is CE. So we have 1/2 E double dotted with this quantity, 2 mu E plus lambda trace of E times the identity tensor. All right, so now just using some tensor properties, we know that E double dotted with E is the same as the magnitude of E squared. Then we also have that E double dotted with the trace of E times the identity tensor. That will give us the trace of E squared. So now we can rewrite the free energy. So we have, so now we can distribute. So we have 1/2 times 2 times mu times, so the 1/2 and 2 will cancel. So we're left with mu times the magnitude of E squared. And then we have 1/2 plus 1/2 lambda. And then we know that E times trace of E times the identity tensor is trace of E squared. So we have trace of E squared. And so here we have our second governing equation, which is for the free energy so our free energy for the linearly elastic behavior of an isotropic material. And so our third governing equation comes from our local momentum balance, which, to recap from previous lecture, is rho u double dot is equal to the divergence of T plus our convectional body force, which again, we now have our equation for E. We have our equation for T that we can now substitute in. So we have the divergence of 2 mu E plus lambda trace of E times the identity tensor plus B0. So I'm going to go ahead and analyze the divergence of 2 mu E and the divergence of lambda trace E times the identity tensor separately. So first we have the divergence of 2 mu E. So we can pull our 2 mu out in front since those are constant, and then the divergence of E so what we have 2 mu times 1/2 our divergence del xj, and then E, which can be expressed as del ui del xj plus del uj del xi. So now we can distribute the so now just distributing the del xj, we have and then the 2 and the 1/2 cancel, we have mu times del squared ui del xj plus del squared uj del xj del xi. And so now symbolically this is equal to mu times del u So that's what this part is. And then we also have the gradient times the divergence of u, which is what this part is. So that's just the first part. So now we also have to consider the divergence of lambda times the trace E times the identity tensor. So again, we can pull out lambda so that we just have the divergence of the trace of E times the identity tensor. So this similarly, it's going to be, so we have the divergence and then trace of E times the identity tensor could be written as del uj del xi. So then we get lambda del squared uj del xj del xi, which symbolically is the same as lambda times the gradient times the divergence of u. So now if we combine 1 and 2, so combining 1 and 2, and substituting this into our local momentum balance. So as a reminder, this is our local momentum balance. We get rho u double dot is equal to mu times del u plus lambda plus our convectional body force term. So then we can group like terms and we get mu times del u plus mu plus lambda times the gradient divergence of u plus our convectional body force. And this is our third and final governing equation for the linearly elastic behavior of an isotropic material. So let me see if I can fit them all. So to recap, we have 3 governing equations. The first one, we can express our stress tensor. I guess just taking a step back for what we've done throughout this whole lecture, we started by recapping some of the key points from the previous lectures, and we started the main content for this lecture by defining our elasticity tensor, and we did this by, let me find it real quick. So we started the lecture by defining our elasticity tensor, and we formed this definition based on our Taylor series expansion for our second Piola-Kirchhoff tensor about C is equal to 1. So once we defined our elasticity tensor, we were then able to, and then once we also took the Taylor series expansion of our free energy, we were then able to form, so we took our Taylor series expansion for the free energy as well, and from there we were able to form our stress strain relation and our equation for free energy in terms of our elasticity tensor as well as our Green St. Bernard tensor, which we used because we are dealing with small displacements and deformations. So then once we formed our stress-strain relation and free energy relation, and then once we also defined our equation for an isotropic body, we were then able to form our three governing equations. The first for stress, the second for the free energy, and the third being our local momentum balance. So again, all of our equations were derived based on two assumptions. The first, that we were working out of a natural that the reference configuration is natural, and the second being that we were dealing with small deformations. So that concludes today's lecture. Yeah, thank you for listening.